All right, so I am now recording. Y'all are welcome to talk, etc. That's not the issue. I didn't want there to be a surprise in that event. So we're looking at example 2003, problem 2, and a simple random sample of adults living in a suburb of a large city was selected. The age and annual income of each adult in the sample recorded. The resulting table are summarized in the table below. What's the probability that a person chosen at random from those in the sample will be in the 31 to 45 paid category? Well, first off, I do want to talk about the table. All right, so row and column totals, these two things are your marginal totals. These represent your marginal totals. Now notice I didn't circle the 207. The 207 is your sample size. Now it could be that your sample was an entire census and covered the entire population, but that's your sample size. So the 207 is the sample size. And then the interior of the table are your conditional frequencies or your joint frequencies, all right? So we have our marginal frequencies as totals. We have our sample size. Some people refer to this as the total because it's everything total up. And then in the middle, we have our conditional or joint. I'm gonna need a better pen for writing on this, but that's okay for today. So it says, what's the probability a person chosen at random from those in a sample will be in the 31 to 45 age category? Well, if we follow that 31 to 45 age category all the way across, we find that there are 89 people in that category. And so that would just be 89 out of 207. So the probability of 31 to 45 equals 89 to 207, and that would be a complete answer and would be full credit. Now you could reduce it to a decimal if you wanted to, and we'll go ahead and do that real quickly because I just want to see how the calculator shows up or whether I want to use the online calculator. 89 divided by 207. And so we get a number of about 0.43, all right? So we get a number of about 0.43. And by the way, if you have a question, cut in, that'd be great. That way I can hear the way y'all mic in as well. But like I said, I'm not posting this. This is for my research. In other words, so that ultimately in the future, other students will benefit, but not from this video. This one I'll delete after today. So what is the probability that a person chosen at random from those in a sample whose incomes are over 50,000 will be in the 31 to 45 age category? Now, we have to be really careful about that. They say that a person chosen at random from those in this sample whose incomes are over 50. So we are looking for, they've got to be in the over 50 category, all right? So if I scroll back up or slide back up, over 50 is here. Well, how many people do we have in the over 50? Well, we have 96. So out of those 96, how many are in the 31 to 45 category? So basically, we're essentially working with a given. So given that it was greater than 50, what's the probability of the intersection of greater than 50 and 31 to 45? And when we do that, we go, well, there's only 96 that were over 50, and that intersection happened to be at 35. All right, so based on your answers in part A and B, is annual income independent of age category for those in this sample? And explain. All right, so there's a couple ways to do this, but specifically they wanted, and I'm going to show you both methods. One would get you full credit, one would get you partial credit. I'm going to show you the full credit one first, which honestly is a little bit more challenging, even though you've done the work. And the reason they wanted the full credit, the way I know which one they want is this is based on your answers in part A and B, which means I need to be using those two. And I'm going to go ahead and reduce that. I'm going to go ahead and turn that 35 divided by 96 into a decimal. And we find out that that's 0.36, about 0.365. All right. So this is about 0.365. You okay with that? All right. So here's what I know about independence. All right. I know that the probability of A given B equals the probability of A and B over the probability of B. This is always true. This is on the formula sheet. This is always true. However, if independent, it equals the probability of A. All right? Well, if I look at part B, right here, that's A and B over B. Okay? A and B over B, and this is A. So basically they're just saying, hey, you know what? If I show that, does 0.365 does not equal 0.43. And that's just because I recognized that this was the same as that, and this is A, okay? Because this is 31 to 45, which is referenced there. By the way, guys, does that make sense on this problem?
Yes.
Or let me back up. Are there any questions on that I might be able to help explain a little better? To me, this was a much more difficult, even though the work was already done for you, this is a more difficult way of conceptually understanding it. I think an easier way to understand it, unfortunately for this problem, it only got you partial credit, is if you use the multiplication rule. And the multiplication rule was this. The multiplication rule says the probability of A times the probability of B equals the intersection. All right? So in this case, we're interested in over 50, which would be 96 over 207. We're interested in a 31 to 40, excuse me, we're interested in a 31 to 45 category, which is 89 over 207. And then we need to know if it equals the intersection, which is 35 over 207. Well, to make that, you know, for me, I don't know those numbers. So I'm going to go ahead and start with 35 divided by 207, 35 divided by 207, and that equals 0.169. And then I'm going to multiply the other two out, all right? Which is going to be 96 divided by 207 times 89 divided by 207. And I get 0.1994. Well, that means they're not equal. All right, because they are not equal, and I should have said this over here, they're not independent. All right, and please note the multiplication rule is only true if independent. This part is always true, but it only equals the probability of A if independent. All right, we good with that?
Yeah.
Thank you, Drew, for your participation. It's greatly appreciated at this time.
You're welcome.
All right. So I'm going to also look at 2010 Form B number 5. An advertising agency in a large city is conducting a survey of adults to investigate whether there is an association between highest level of education and primary source for news. The company takes a random sample of 2,500 adults in the city. The results are shown in the table below. Then it says, if an adult is to be selected at random from the sample, what's the probability that the selected adult is a college graduate or obtains news primarily from the internet? All right, so here they use the word or. So, but we also want to know, are they a college graduate? Or do they obtain their news from the internet? Well, that's great. All right, and the keyword. So we were looking for a probability. We're not looking for a frequency, and we have the word or. Well, there's a little thing tricky about this problem. Or means, or in statistics typically mean, or in probability means add. Well, the formula for addition is in probability is a probability of A union B, union just means or, equals the probability of A plus the probability of B minus the probability of A and B. All right. Well, if we say A is the probability of a college graduate, we're going to end up with 693 over 2,500. The probability of internet is 687 over 2,500 minus, and this is what was tricky, is the intersection, 245 over 2,500. All right, so going about our math, 693 minus 687 minus 240, oops, it'd be nice if I put addition in there, 693 plus 687 minus 245 is 1135. So our answer would be 1135 over 2,500. All right. Now here's why this is. Okay, this is what's happening. If I were to draw, and I'm going to try to attempt to draw this Venn diagram. I did not make a big enough overlap. Oh well, I'll make it work. This is I for internet, this is CG. Well, we know that the total number of people using the that are college graduates are 693. I know that the total number who use the internet are 687. But I also know that 245 use both. So that means the part that's in the circle is going to be 693 plus 245, or 693, sorry, 693 minus 245. So this is going to be 448. Then we have those who use the internet. That's going to be 687. But of those, 245 are college graduates, so I need to subtract that out. And that's 442. And if I add up this number plus the overlap, so 448, 442, and 245, I actually find out how many students there are. The reason I have to do the subtraction is because if I don't, there'll be double counting. All right. If the adult who is a college graduate is to be selected at random from the sample, what's the probability that the selected adult obtains news from the internet. Well, now they're saying, okay, the adult is a college graduate. So we have a given, all right? So given that they're a college graduate, well, how many college graduates are there? We have 693. And then they want to know the intersection. All right, well, the intersection is going to be the intersection of internet and college graduate. We have 245 of those. So that would be 245 or over 693. We okay with that? So following along, when a selected adult at random from the sample of 2,500 are the events is a college graduate and obtains news primarily from the internet independent. Well, you actually have a couple choices on this. You can sit there and run this as a proportion and see if it's proportional. But I would prefer if you used either the multiplication rule or the conditional rule. Once again, the conditional rule is this: the probability of A given B equals the probability of A and B over the probability of B. This is always true. 100% of the time, that's true. But if they are independent, or if I want to check for independence, it has to equal the probability of A. Well, we just did the conditional. So we have 245 over 693. And in this case, we'd already done and said, is a college graduate or obtains news from the internet. What's the probability they obtain news from the internet? Well, 687 over 2,500.
Mr. Spencer,
Yes.
can you scoot your page up?
Excuse me?
Oh, before your page wasn't scooted up, so I was wondering if you
Yeah,
could
I'm sorry about that. I just looked, when I heard your voice, I looked up and I said, oh, it started sliding it up. Okay. So this part's always true. This right here was the conditional that we found here. And then we needed to know what's the probability of a college grad, that they use internet. Well, the probability someone uses internet is 687 over 2,500. And I haven't done the math to show it, but trust me on this, they actually are not equal. And they accepted it, this time they accepted it for full credit. They accepted the multiplication rule for full credit, which is the probability of A times the probability of B equals the probability of A intersect B. And again, I think this is an easier way to understand for most of my students, not all, is 693 over 2,500 times 687 over 2,500. And then we need to check to see if that equals the intersection, which is 245 over 2,500. So 245 divided by 2,500 is 0.098. 687, and then I'm just going to multiply those two together. 687 divided by 2,500 times 693 divided by 2,500 is 0.076. Those are not equal, therefore they're not independent. Now, you can't just stop with the not equal. You need to actually take a moment and go, because they're not equal, therefore they're not independent. Now, and I ran out of room, but therefore not independent. All right? Now, you're probably going, well, wait a second. They only gave me full credit for using the multiplication rule here, but on the previous problem, they only gave me partial credit. What was the difference? All right, so let's figure that out. Okay? So on this problem, did they tell you what to do? They just said, hey, are they independent? They didn't tell you how to approach independence. They just said, approach independence and let us know if it is. All right? Here, they gave you some direction. They said, based on your answers in part A. In other words, using what you've previously done, let us know if they're independent. And because they wanted you to refer back to what you previously done, if you had used this, you got partial. If you'd done it this way, which was based on what your previous work is, you could receive full credit. Does that distinction make sense? I believe it did. So I'm going to go with it does. All right. Now, I know that we are working with independence right now and talking about displaying and describing data. And so part D doesn't technically apply to what was in this section, but we should know how to do this at this point because you all have covered all the topics of the year. So the company wants to conduct a statistical test to investigate whether there is an association between educational achievement and primary source for news for adults in the city. What is the name of the statistical test that should be used? So here's the key word. We know that they're looking for a statistical test and they want to know if there's an association. So in other words, they want to know if they're independent or not. Well, we've already said up here that they're not independent. So if they're not independent, that means there is an association. But what type of test is it? So what type of test do we run to determine whether or not we have something that's independent? Well, typically speaking, if we have a table and we're looking for independence, we're going to run a chi-squared test of independence. All right, so this would be a chi-squared test of independence. And they actually gave us another hint. What are the appropriate degrees of freedom for this test? Well, remember, for a chi-squared test of independence, it's rows minus 1 times columns minus 1. So we have 1, 2, looking up the table, 1, 2, 3, 4, 5 rows and 3 columns. So scoot up just a little bit farther. 5 minus 1 times 3 minus 1. Using advanced mathematics, I get 4 times 2, which equals 8. Okay? All right. So all right. The table below shows the political registration by gender of registered voters in Franklin Township. Given that a randomly selected registered voter is male, what is the probability that he is registered for party Y? So once again, we have a given. So we know we're going to be looking for an intersection on top. And the given is male. And we're going to look for the intersection between male and party Y. And I'm just going to put male and Y. Okay. So they told us male. So we have 200 who are male. And we're looking for the intersection, which is 48. By the way, I have a question. This is a dumb question. Because I thought something was going to be showing up on the screen that I'm not seeing on the screen. Do you all see my face on the screen at all?
Yeah. Yes.
Okay, I didn't know if it showed up or not. It doesn't, to my surprise, it doesn't show up here. I thought it would, but it doesn't. And oh well, it is what it is. Okay. So thank you. So 48 out of 200. All right. So did I do that right? Yes, I did. So 48 out of 200 is 0.24. Among the registered voters for Franklin Township are the events is a male and is registered for Party Y, independent. All right. Well, once again, you can do this one of two ways, but I'm just going to go ahead and use, since they did not specify which method to use. I'm going to go ahead and use the multiplication rule, which would be probability of A times the probability of B equals the probability of A and B. And since I have room, I'm going to go write if independent. All right. Well, probability of A would be 168 over 500. Probability of B is 200 over 500. And then this should equal 48 over 500 if independent. So going back to the handy calculator, and then we have 168 times 200. I don't want to do it that way. 168 divided by 500 times 200 divided by 500. 0.1344. Those are not equal, so we are not independent. All right. In Lawrence Township, the proportions of all registered voters for parties W, X, and Y are the same as for Franklin Township. All right, so let's just look at that. Well, what was for party W? We have this. Oops, party W, we have 88 out of 500. So party W, the proportion is 88 out of 500. And if I want to turn that into a decimal, because sometimes that's easier to understand, 88 divided by 500, 0.176. All right, party X is going to be 244 out of 500. And then party Y is 168 out of 500. Let's go ahead and get the decimals for those. Now, I'm going to just do a really quick check. Because that's everybody, that should sum up to within rounding of one whole. And if it doesn't do it, then I made a math error. So 0.176 plus 0.488 plus 0.336. Fortunately, I added up to 1, so I did things right. Okay, so in Lawrence Township, the proportion of all registered voters, so W, X, and Y, are the same as Franklin. And party registration is independent of gender. All right, so complete the graph below to show the party to show the distribution of party registration by gender in Lawrence Township. Well, they tell me they're independent. If they're independent, they're proportional. And consequently, my segmented graph should be the same for all. Now, I don't think they actually labeled W, X, and Y on the actual graph, but I'm going to, or I did it already. If you were drawing this graph on the test and they had not labeled it, you would need to do so. So party W, 0.176. Well, this is 10, this is 15, so somewhere in between here. And I'm just going to use, and because they're independent, I know that the male and the female have exactly the same number. And it represents 0.176. Party X is 0.488. So I need to take the 0.176 plus 0.488 because it's a segmented, and ultimately we're going to make a segmented bar chart, and ultimately it's going to add up to one whole or 100%. So I came up with 0.664. So 0.6, 65, so something slightly over 65. All right, and I'll just draw a couple of horizontal lines. Well, the rest of this should be party Y, and I don't know, maybe I'll just do a backward slash, a backwards candy cane. And now I have a segmented chart where all three sections, when they're combined together, is 100%. And because they have the corresponding segments for male and female are the same, we have a good indication of independence, because if they're independent, they will be proportional. All right, I have one more thing. Actually, I guess I have two more things I wanted to do. I wanted to talk about this problem because this one gives people fits. And when I just talk about it, it doesn't make as much sense as if I show a little bit of work. So administrators at a state university computed the mean GPA grade point average for juniors and seniors majoring in either physics or chemistry. The results are displayed in the table below. When juniors and seniors are grouped together, could physics majors have a higher mean GPA than chemistry majors? Well, when I look at this, I'm like, my initial reaction would be no. Look, the chemistry majors are smarter for juniors and are doing better for seniors than the corresponding physics. But then they ask the word, could it happen? It's like, well, maybe. It depends on numbers, all right? And basically that refers to the thing called Simpson's paradox, which is mentioned directly above it. When the results from combined grouping appears to contradict the results from individual groups, all right? And basically, if all of a sudden we go, hey, you know what? Physics actually had a higher GPA than chemistry, that would appear to contradict what we see. Because what we see is like juniors and seniors are chemistry majors did better for juniors and chemistry majors did better for seniors. That's what we see. But is it possible that physics majors actually have a higher mean GPA? Well, that could happen. Whether it does happen depends on the sizes of the subgroups, all right? So here we go. I'm going to try a couple things out. For ease, we're going to say that there are 100 juniors and 100 seniors, all right? And as it turns out, we only had one junior majoring in physics. And we happen to have 99 juniors majoring in chemistry. On the other hand, we had 99 seniors majoring in physics, and for whatever reason, they only had one senior majoring in physics. Okay, so with that in mind, let's find out what the average physics is. Well, physics would be 1 times 2.8 plus 99 times 3.2. And when I do that, 1 times 2.8 plus 99 times 3.2, I end up with 319.6 divided by 100, and I find out that I have a 3.196 GPA for physics. Doing the same thing for chemistry, we have 3.0 times 99, and we have 3.6 times 1. So 3 times 99 plus 3.6 times 1 is 300.6. And if I divide that by 100, I get a GPA of 3.006. And it's like, oh, hey, chemistry was 3.196. I mean, physics was 3.196. Chemistry was 3.006. It does appear that physics outperformed chemistry. Why did this happen? Well, it happened because of the way the seniors and juniors were apportioned, all right? Because a ton of seniors took physics and very few took chemistry, whereas on the juniors, a ton of juniors took chemistry and very few took physics. So my answer is yes, it could happen. Whether it does happen depends on the number of juniors and seniors in each major, right? It could happen. We just showed that it could. All right, stem and leaf plot. Now this is the only part of this thing. This was a whole long description that they asked us to do. What they really asked us to do was, and you know what, before I do this, let me check something. They asked us to compare 3 rivers. This is actually in your note spiral. So this problem is actually in your note spiral along with all the description part. But I wanted to sit there and show you how you could use the calculator to help yourself out with this. So I went ahead and I entered all that data into column L4. All right, so all that data is entered into column L4. And they want me to make a stem plot. I don't know about you guys, but my experience is I always leave data out and end up with a problem. So I'm going to go ahead and input it all into my calculator, which I did, and I put it all into L4 just because I had some other things in there. And I'm going to go to second list. I move over 1 to operations, and the very thing says sort ascending. I'm going to select that, sort ascending. And what column do I want? I want L4. And then I'm just going to press enter. It says it's done. So I go back to stat edit. And now when I look at it, it's all in order from least to greatest. Okay? And if I scroll down, I go, okay, I have some numbers. I have some numbers that start with 3, some that start with 4, some with 5, 7, and 8. I don't see anything with 6s. Okay? So 3, 4, 5, 7, and 8. Well, even though it's a stem plot, essentially I have a number line. So my number line in this case, 3, 4, 5. Number lines don't skip numbers even if one's missing. So even though I didn't have any 6s, I'll write it down. So 3, 4, 5, 6, 7, 8. So 3.4 would be 3, 4. The next number, 3, 7. And I just stack it. Then we have 4. 4 doesn't have a number after it, so it must have been a 0. It must have been 4.0. Then I have 4.2, 4.3, 4.6, 4.6, 4.7, and 4.8. 5.1, 5.3, another 5.3, a 5.5, a 5.6. Now, there's nothing on 6s, right? Because there's nothing on 6s, I'm not going to have a value there. I'm not going to put a 0. There's nothing there, all right? Then I have a 7.3, a 7.5, an 8, again, because it must be 8.0, an 8.2, an 8.6, an 8.7, and I think that's it. All right, so there's my stem plot, and I need to do one more thing. I need to take a number, and it doesn't even have to be a number. So I could write 6 line 3 equals 6.3. I have to give a key, all right? And if you have something like this, it's like, hey, you know what? You're going to say you're going to have a gap at 6, all right? So nothing at 6. Okay, I think that's all I wanted to actually go through. I'm going to stop this recording, mess with this later, see what happens with it. It's not stopping that way, so I'll go to more, stop recording.